sections 6.4 through 6.5. And what this is that now we're finally ready to start in on some scattering problems and some tunneling problems. Okay. So essentially what the heck? That was weird. For some reason, my computer just kind of wigged out a little bit for a moment. Essentially, we have something like figure 612, which is this figure right here. And in the past, we've talked kind of sort of about these bound states, albeit we did it predominantly with a square well. And then in some sense, we've talked about unbound states, but with a single flat potential that we've just said is equivalent to V equals 0. Okay. Worth noting, the bound states they have quantized energies. The unbound states do not. Okay. The bound states fall into energy E is less than potential energy V. And so they end up having to fit into the well. And so not only do they have these quantized energy values, but they're also very much normalizable and so on. Anything that's up here, unbound, doesn't really have to fit in the well, and therefore doesn't have to have quantized energies. Remember that energy quantization was in some sense a consequence of having to fit within the well. And you can review your quantum 1 notes for like what the whole argument of that is. And so what we're going to do is we're going to actually we're going to kind of begin with a simple case, one where we just are going to have scattering from boundaries. Okay, so if you're looking at a well, there's usually two boundaries. Okay, and so in one dimension, the scattering could take the form of, say, reflection by and transmission across each boundary. And then once we've done that, we can consider a second effect, which is tunneling through potential barriers. Okay, so the state that we're looking at to begin with is one that's more or less like this, in which we have some minimum potential energy, like this right here is going to allow some scattering. And we're considering energies up here somewhere. Okay, so we're considering energies greater than or equal to 0, let's say. And so for this system right here, what you have is something that says, you know, V of X is 0 if X is less than negative A. It's negative V0 for minus A less than or equal to X less than or equal to A. And it's 0 again if X is greater than or equal to A. Okay, and again, you're looking here at figure 6.13 from the McIntyre text. And I'll even just sketch it here so that you've got it when I upload these notes. This is your V of X, even though I've already shown it. This is your V of X axis. Maybe this right here is our X axis. And then the potential energy itself is basically just following this. drops to some value, comes over, comes back up to the x-axis here. And so this is my actual v of x function. These are my axes, and then the value here would be negative v naught, and this would be a and minus a. Okay, for this choice of energy, if E is less than 0, it's going to be a bound state. If E is greater than 0, it's an unbound state. If E is exactly equal to 0, then somehow we have that transition from bound to unbound. But with that said, E equals exactly 0 may not, and in fact, I would argue is not the value of any of the bound states. So you could in some sense say that this is where the equals in this inequality has to go, because this is a continuum, but these are quantized, and E equals 0 is not one of the allowed quantities here. And to answer like, why is that? I would say, okay, go back and review what your notes say about energies in a square well. So given these, this is what our sort of energy eigenvalue equations are going to look like. The Hamiltonian operator on the energy eigenstate. Yeah, we'll go ahead and use a sub E here. Is the energy value times the energy eigenstate of X. Okay, so that of course is your eigenvalue. And then we ask, what is it that the Hamiltonian is doing? Well, essentially this Hamiltonian operator has to be as follows. It's either negative h bar squared over 2m minus v naught, or, whoops, I kind of left off the important part, didn't I? D squared by dx squared minus v naught. Or it's negative h bar squared over 2m d squared by dx squared plus, or if you'd prefer, minus 0. And that's for absolute value of x less than a, so inside the well or above the well, whatever you want to call it. And this one right here is outside or not directly above the well. Okay. So our unbound states. Since E is greater than 0, then we expect a sinusoidal solution. We expect that based on our discussion of the last couple weeks. And we expect this for both regions. both regions, you could say this is all three regions if you want, both regions being this or this. But remember that this one right here is actually two regions. Okay. But these two regions basically would correspond to having either this right here, 2m e over h bar squared, or 2m e plus v naught over h bar squared. Okay, so our energy eigenvalue equations in terms of wave packets and in terms of these two, they're going to become like this. Let's say d squared by dx squared of our energy eigenvalue state, and that's negative k2 squared psi e of x. Let's actually do it like this. Let's do it twofold like this. Okay. So these are your two equations that you're solving. I don't know if this is superfluous to do like this. Maybe I will just do this. It's not like it's that much extra writing. Okay. And so then the solutions to this would have to have this general form. And now I will use this. A e to the I k1x plus b e to the negative I k1x, c e to the I k2x plus d e to the I negative I k2x, and then f e to the k1 a1x, and g e to the negative k1x. And again, these are for the regions x less than minus a, minus a less than or equal to x less than or equal to a, and x greater than a. Pretty this one up a little bit. Sorry for the small handwriting here. Okay. So now the question is, how many equations do you see here and how many unknowns are there? Well, in some sense, what's that?
3 equations and 6 unknowns.
Close. You almost had it. It's 3 equations. It's actually not 6 unknowns. It's actually 7 unknowns. So there's a little bit of a bait and switch here as to what counts as unknowns. 1, 2, 3, 4, 5, 6, 7. We don't know what the energy is either. So 3 equations, 7 unknowns. And yes, you'll notice that I skipped over the letter E when I'm making these coefficients. So it's symbols A through G. It's just that E happens to represent something other than the other 6 symbols do. But those are your unknowns. Okay. So now we say, what do we do about it? Well, if these were bound state problems, what did we do about it? Well, we basically said, fine, if they're bound, then that by definition means that they have boundaries. And across a boundary, we need continuity of the original equation and we need continuity of the derivative of the equation. So as it turns out, that got us, or would get us for this, 6 equations. 6 independent equations, and then normalization gives us a 7th equation. And so in principle, you could go through and solve for A's, B's, C, D, E, F, and G.
Wow.
With the finite square well, which this basically is a finite square well by definition, this was a pretty long process. It was not a very short process. It took us several days to kind of grind through the solution. And ultimately, we didn't even actually explicitly solve it with an analytic solution. We didn't just get an equation that says this is the answer. We had to actually use transcendental equations, and eventually we either solved it numerically or solved it by graphing. And so you kind of get numerical answers one way or the other, which are fine. Like that, if that's what you have, then that's what you have. They are answers, but they're not anybody's really favorite thing to have as an answer, right? It's kind of the humor of physics. In physics 1 and physics 2, you want numerical answers. Everything's got to have a number to it. And then as you get more advanced in physics, we realize sometimes it's nice to not have a number, to just have a formula, and then you give me numbers at some point and I can just tell you what the answer is. Well, now we're back to it has numbers and you will have to do it. You're going to do numbers and you are going to like it or not, you know? But that was for the bound case. Now we have the unbound case and we have to say, what are we going to do about that? Because there are kind of sort of boundaries here. Like there's certainly a transition that must happen from here to here and from here to here. But they're not boundaries in the sense of being turning points, let's say.
Dr. Sanders, in order for all this to work, does the mouth of the well have to sit at E=0? I mean, does the position of the origin matter? It's not intuitive.
Oh, here?
Yeah.
No, you could put it somewhere else, but also like then you're just creating more work for yourself, right?
Right.
Like I guess you could the other logical possibility is let's put the bottom of the mouth at the bottom of the well at equals 0. And
Right.
so the minimum is V0 and everything else is therefore at plus V naught. And in some sense, what that does is it reverses these equations by this now becomes plus 0 and this becomes plus V naught.
Mm-hmm.
But now you run into unbound is E is greater than V naught. And bound is E is greater than 0, but less than V naught. So you've sort of added some conditions there. And then when you go to do this solution here, this now has to be essentially,
It need to be like E minus E naught.
yeah, it'd basically be like an E minus V naught and an E over here.
Yeah.
And yes, it still works. And even like that simple change may not do too much to what we're doing here. But like any other choice, you're going to end up with like, let's say that we say, okay, well, it's halfway between. All right. So the well opens here at plus V naught over 2, and it bottoms out at minus V naught over 2. Well, now we change these conditions to have V naught over 2's in them. We contain, this one would now have a minus V naught over 2 and a plus V naught over 2. But then when you get down to here, you end up with 2m E minus V naught over 2 and 2m E plus V naught over 2. Like you can see where now we're
The math
having
gets a lot
to,
more complicated.
yeah, and in principle, all of these solutions give us the same thing. We're just kind of offsetting what we called 0,
Right.
but having to write all the extra stuff, it's like, well, look, potential energy in general rule for all potential energy problems, you get to decide what counts as 0 for your system because you're just doing delta V's ultimately. And so let's pick the most convenient thing where we do the least amount of writing and the least amount of keeping track of what the boundary is going to be or what the conditions on the boundary are going to be. That will be our sort of ideal solution. Actually, this is kind of a good stopping point. We're right at 1150. And yeah, like next time we can start off with different types of scattering solutions. So different kinds of conditions for how are we going to get A through G.
So is this time for questions?
Yeah, I think so. I think
Okay.
so.
So in the real world, there's no such thing as a square well, right? It's a euphemism for something that we're trying to model, right? And is
Yeah,
that
to some extent.
is is that a hydrogen
You
atom?
no, no, it's not a hydrogen atom. In fact, in when we introduced this in chapter 5, we kind of explicitly compared this to what you get for a hydrogen atom.
Right.
They're not the same. For
Okay.
one thing, like taking an infinite square well, for example, because remember the finite square well, if we're looking at bound states, the finite square well bound states, each level you go up, you're going up by n squared. Hydrogen atom, each level you go up, you're going up by essentially 1 over n squared, if
Yeah.
you will. And so what that means is that the hydrogen atom kind of has a bottom, but then its top starts getting very crowded. And, once you get to E equals 0, you've ionized.
Right.
But in the infinite well, that's not how it works at all. You just keep going up and up and up and up, and there's infinitely many levels, and they get farther and farther apart.
But there's no such
And
thing as an infinite well, though. That's
sure, but
just
for a finite well, you keep also going up and up and up, basically by n squared each time. So
yeah.
again, levels are getting farther apart as you go up, and eventually you can escape from the well, and that's kind of analogous to ionization. But you're looking at n squared versus 1 over n squared, and positive versus negative, if you will.
So then a finite square well is an arbitrary model that's simple enough to understand for an introductory course, but the real world is a little more complex.
Um, kind of. Like there are things that are very you can make a potential that does approximate a square well. Now, with that said, I would contend that it's kind of difficult to force it to be one dimensional.
Right. Oh, for
Um,
sure.
and in fairness, by analogy, like look in optics when we learn the double slit, right? So
Yeah.
the double slit experiment, we treat them as if slits have dimension this way, but they're infinitely far this way. But in reality, that's not how they work, right? Like they're this long this way and comparatively they're this wide. And we say that's a slit. And then usually we try to make the spot so that it's big compared to this, but smaller than this. And the approximation tends to work out pretty well then.
Yeah.
Um, and so something similar kind of could happen here. Put differently, you can always try to create new functions from an existing old function by superposition. But how much effort do you want to put into it to force the damn thing to be a square or a flat top or something like that? If you have sine waves that you can superpose for your analysis, very easy. If what you're trying to do is create a flat top from, say, a linear expansion, okay, so we do a Taylor expansion. We figure out what the Taylor expansion terms are for that. Not quite as easy, but still manageable.
Yeah. So in real life, then and I'm trying to think. Okay, well, it's not just a particle; it's a photon. Like there's all other types of things we can use this type of logic to understand. But in reality, with an electron and a nucleus of some kind, most of these things ultimately have to be modeled in spherical coordinates, I would imagine. Right. To your point about the single dimensionality of a square well.
With atoms, yes, you usually end up with spherical harmonics, and you're
Yeah.
usually in spherical coordinates. Sometimes it's still practical to model in some other dimension.
Yeah.
Um, and it's again all things like what did we choose for our basis? What did we do? What coordinates do we want to use? Any of that. It's usually contextual. Um, Put differently, if I wanted to model waves being emitted from a point source,
Okay.
I'd probably prefer to do that in spherical coordinates
Sure.
because the wavefronts propagate as spheres.
Right.
But if I had that same problem of I want to model waves, but instead of a point source, I have a line source or a whole bunch of point sources along a line.
Yep. Sure.
I actually don't want spherical anymore, and I don't want Cartesian either. I want cylindrical. Because for most of that wave, the propagation of the wavefront will look cylindrical. And likewise, if I have a plane emitter, now I probably want Cartesian.
Right.
Although, I guess you could argue that cylindrical works just fine as long as you've chosen this way to be the z direction. It's just a little bit more of a eccentric way of doing it, in my opinion.
Yeah, and I think this is where I struggle with quantum mechanics in general. Because if you're electrodynamics, you're like, hey, there's a particle has such and such charge. What's the field over here? Well, all of that are things that I can picture in my mind. Whereas with the quantum stuff, I have a difficult time deciding what it is that I'm trying to picture.
That's probably a good thing.
Okay, okay,
Usually the
that's
mental
reasonable enough
pictures are
then.
not good. Um, one way that I kind of approach it, and as with anything like this, your mileage may vary.
Right.
I try to think of what is the experiment. Like if there's an
Yeah.
experiment that can go with it, what is the
Right.
experiment? What does the setup look like, and what is the output doing?
Yeah.
Like with spins, I don't try to anymore. When I first started out, I maybe did, but it's futile to try and have this is what a mental picture of spin looks like.
Right.
But you can have a mental picture. This is what a Sturm Gerlach experiment looks like.
Yeah.
And so physically, I have, let's say, an electron or a silver atom was what they usually originally used. But we could say I have an electron. Never mind that there's some uncertainty in position and momentum. Let's pretend for a moment that we know those two things precisely enough. You can go look it up. It turns out we don't. But
Yeah.
let's pretend that we do for a single electron. And now I put a magnet, and the north side is here and the south side is here, and one of them is shaped like this, one of them is shaped like this. So I've got a non-uniform field. And now it goes through that field, and now there is sort of a torque on it. There's actually a net force on it because
Yeah.
it's a non-uniform field. And as a result, there's a deflection. Either it goes up or it goes down. And my spin is telling me, did it go up? Did it go down? And by the way, how much did it go up or down? How much did it go up or down?
Yeah.
And how much did it go up or down is a combination actually of what was the spin and also what was the speed and therefore duration of interaction. But that's neither here nor there.
Yeah. There's so many questions that I've got. Okay. One last question because we're out of time already, but that is when you try
Oh,
to
don't worry.
picture.
If I let Sam in on this, we will double the number or may double the questions and may have Sam asking questions on your questions.
Well, let's bring Sam in because I'm all about it. But
And and,
Mike,
and
what do you
if
try to?
Martin was here, he usually also has, but his are slightly different than the ones you're asking. So
So
that's why I originally wanted to have like, you guys and you guys all have questions and you all ask them, they're good questions. But like imagine having a class with 12 people and on any given day 3 people have questions that they want to answer. And like, yeah, it means we don't get to answer everybody's question,
right,
but boy, this
the
becomes a
learning.
nice discussion class.
Yeah, no kidding. Well, I the first couple of lectures that we did here, I've kind of figured out for myself that I need to save my questions till the end, or we won't be able to cover the material, right? So,
Yeah. Well, and
um,
and the thing with the questions is this. It's more work for me, but it's also more fun for me. And I hope it's more work for you, but also more fun for you to do it that way. And
yeah,
sometimes I just don't know the answer and I'll try to let you know if I don't. Like I'll
yeah,
say I'm
and maybe we'll
spitballing or
get to
I'm
the point
guessing or naively.
where the answers maybe aren't even known, right? But
Sure,
in
sure.
the square well model, if I just try to picture a hydrogen atom and an electron, right?
Uh-oh.
Then
Hang on a second. Somebody's banging on my door.
sure.
Close the door. Yeah, no problem. You have to have the stop. See you later. Somebody left something here.
And
Okay, sorry. So you were asking.
yeah, yeah. So, and maybe this question is better left for next week. And if that's so, that's an answer that I of course will accept. But when I'm picturing a hydrogen atom and an electron, and so my E reaches some threshold, and now my electron is free, that atom's ionized, right? It's only a proton now in space. That makes sense. But when you get to things like tunneling, so for that electron, in my mind, that's a vertical boundary. You know, it pops out of the well and it's free, right? But what is that left and right boundary? What is that?
So sometimes, not always, you have a boundary that is analogous to, let's say you have like a molecule, or
Yeah.
let's say that you have a crystalline lattice or something. And so there's potentials that are in some places higher and in some places lower. And so maybe you happen to have one hole in the lattice somewhere. So you have one electron that's been removed. And so in principle, like this electron is bound to this atom. This one's bound to this atom and so on. And maybe this one doesn't have one bound to it. In principle,
Okay.
this electron can hop over to this atom. You've now ionized this one. You've now filled this one. That's one way. Another way of looking at it is that, and we'll see this when we get into hydrogen atoms and into all of the stuff with angular momentum and so on. If you look at it as just a Coulombic potential, then we all know what the Coulombic potential looks like. It's smooth, flat, it comes up like this, and it ends. But for some atoms, or for some, let's say, modifications to your potential, you may have something that looks more like this. Let's say that this is R, this is your potential.
We're not seeing your presentation anymore.
Right. Sorry. I stopped sharing it. This is now going to screw up my potential drawing, but occupational hazards. Okay, so you can sometimes get one like that. You can also get one in principle. I'm not trying to have it loop back down. I'm trying to make it asymptotic to a line that doesn't exist over here because I didn't draw it far enough.
Yeah.
So, this right here would represent a bound state by this potential.
Yep.
This right here would also represent a bound state by this potential of, by the way, the same energy. Agreed?
Yep.
So you could have something that's on this state that somehow tunnels through this and ends up in this bound state.
Okay.
That's sort of like, I don't want to say classical tunneling, but in a different sense of the word classical tunneling,
Yeah.
that's quantum tunneling, sort of like the classic example of it, is
So
a
what we're
potential that looks like this.
so what we're easing up to here really is complex systems where it's multiple electrons, multiple atoms, and we're just sort of at the very early stages of starting to understand it, right?
Yeah, well, in some sense, we never leave the early stages of understanding it.
Okay.
Um, I was
Because
going
reality is
to,
going to get so complex that it's got to be unmanageable.
at some point. Um, Trying to remember what it was that I was gonna look up. I want to say that I have some figures somewhere. Yeah, okay. Um, Essentially, for what it's worth, these different wiggle states are basically because you have a potential energy, but you also have some sort of, like I'm drawing loops like this, like something's physically orbiting like this. It's not necessarily doing a circular orbit, but you have an orbit, and therefore there is some angular momentum to it, and therefore there is some kinetic energy to it, and that will tend to modify what your energy looks like for your system. I'm trying to see if I happen to have anywhere uh-oh, a good diagram. I may not. Grumble, grumble, grumble. I'm not sure that I've got a very good diagram of it to really illustrate the point that I'm trying to make, unfortunately.
Hey, I'm
And
gonna go ahead
I
and
hate
leave
trying
so
to
I can
draw
go get
things.
food.
Yeah, sure, sure. Yeah, I'm
All right.
gonna have to get off and do food pretty soon too.
Sure.
All right, see y'all.
Bye,
Bye,
Colin.
Colin. So are there people that get through quantum and just decide not to believe it?
Yes. Hang on a sec.
Is that
See,
a
now
reasonable
we're getting
position?
really off the beaten path, but yes, there are. I usually they're well outside of the mainstream.
Yeah.
You know, there's people who are their shtick is, can I disprove quantum? And I think that they're not going about it in the right way, in as much as like, look, the predictions from this are too accurate for too many things for us to completely say this has to be thrown out.
Yeah.
But it may well be that we discover that there's some other theory that describes stuff better, that approximates quantum mechanics in some sense, and then approximates classical mechanics in some other sense.
Yeah.
Much like we say, like, classical mechanics still does a great job of predicting stuff for the regime that it's in.
For most
And
systems. Yeah.
yeah, and like quantum mechanics kind of devolves into classical mechanics statistically, is
Yeah.
maybe one way of saying it.
Yep. Yep.
Um, so, it may be that there is something like that below quantum mechanics that you can get to. And, on the other hand, there's different interpretations of quantum mechanics. And, is the Heisenberg, maybe I should say, is the Copenhagen interpretation, which is sort of the prevalent one, is that the correct interpretation? I don't know. I actually am not convinced that that one necessarily is. But that is not a question that we have any way to answer at the moment. Like, nobody's come up with a way of testing. So is Copenhagen correct? Is many worlds correct? Is pilot wave theory, is that the actually correct way to look at it? What's the driving mechanism? We don't
Yeah.
have any way, like, we don't even have a prediction. We don't have a theory that predicts for one or the other that we could in principle develop a test for. We don't have a built inequality to distinguish between pilot wave and Copenhagen at the moment, or Copenhagen and many worlds.
Yeah. I just started looking into Bell inequalities. You mentioned it, and I've made a note to look into that a little bit. But it's interesting. I mean, anyways, the assumptions would need to be validated, and then to say, well, it's